in your class yesterday, we left off setting up this chart, yes? Talking about the idea that if a pair of dice is rolled, okay, you're rolling two separate dice. When you roll the first die, your options are 1 through 6. When you roll the second die, your options are 1 through 6. Now, what we looked at, and I just went ahead and left the chart up here from my first period class. But so if you roll a 1 on the first die, what can you roll on the second die? If you roll a 1, you can roll a 1 on the second die. Or if you roll a 1 on the first die, you could roll a 2. Or you could roll a 1 and then a 3. A 1 and then a 4, a 1 then a 5, and a 1 then a 6. Okay? Now, change up the first die. What if instead of rolling a 1, you roll a 2 on the first die? What could you roll on the second die?
A 1.
You could get a 2 with a 1. Or 2 with a 2, 2 with a 3, 2 with a 4, 2 with a 5, 2 with a 6. Is the chart making sense? Okay? You've got a row where if you roll the 3 first, paired up with 1 through 6. If you roll a 4 first, paired up with 1 through 6, a 5 paired up with 1 through 6, and a 6 paired up with 1 through 6. Now, some of you are going to say, I don't need that chart. I can figure it all out. I just think this organizes us. I think it makes it a little bit easier. I will say this is a common probability question, is to have it being about rolling a pair of dice. So with that in mind, I want the chart to help us figure out what we're doing. Okay, hopefully you have the chart or you're getting it. First question, the probability of getting a sum of 5. Thoughts here, probability of getting a sum of 5.
There's 4 things on that.
And what are those 4?
1 and 4, 2 and 3, 3 and 2 and 4.
Okay, and this is one reason it's helpful because it's so easy to say, 2 and 3 and 1 and 4. But if there's 2 dice, could those be reversed? And they could. So there are 4 pairs out of how many total pairs?
36.
36. And what do we know about 4 out of 36? It reduces to be 1/9. And I'm just going fractions on this section. So I'm just going to leave it as 1/9. Some of you are saying, I could have done that without the chart. Okay, fair enough. Not going to argue it. Okay. What about B? Probability that the sum is an odd number. Thoughts?
1 and 2.
Okay, so 1 and 1 is even, right? 1 plus 1 is 2, that's even. 1 plus 2 is 3, that's odd.
1 and 4.
Okay, 1 and 3 is even. 1 and 4 is odd.
1 and 6.
1 and 5 is even, but 1 and 6 is odd. Are you seeing a pattern here?
Every other one.
Every other one?
Yeah.
Is it? I mean, you can check yourself. Is it going to hold true? 2 and 1. What else?
2 and 3.
2 and 3. And 2 and 5. It's every other pair that's going to be odd, isn't it? Can you generalize your answer?
18 out of 36.
Okay, 18 out of 36, which ends up being 1/2. Now, I could definitely agree if you're going to say, I definitely did not need the chart for that one. I'm with you. I get it. It's going to be half the time. Okay, so 18 out of 36, which does reduce to be 1/2. Okay. Next one. Sum is less than 4. What do you got for sum less than 4? 1 and 1, 1 and 2, 1 and 3 takes me to 4, doesn't it?
2 and 1.
2 and 1, 2 and 2 takes me to 4, and
3 and 1.
okay. So how many that are less than 4? There are 3 out of how many? And what is 3 out of 36 reduced to? 1/12. Okay. Time to change it up. These are too easy for you. Okay. Probability that the sum is greater than 9 or that the numbers are the same. Did you catch that? We've got two pieces going on here, don't we? So, probability the sum is greater than 9. Let's figure that out first. What do you have in the way of a sum greater than 9?
1 and 1.
That is less than. Oh, I thought you were saying like that.
3 and 6.
Or no,
4
never
and
mind.
6.
That's the same. I was talking about the second.
Okay. Can we talk about 4 and 6?
Yes.
I mean, here's check, okay? My biggest sum on this row is 7. My biggest sum on this row is 8. My biggest sum on this row is 9. Here we're at 10. What else is greater than 9? 5 and 5? 5 and 6.
6 and 4, 6 and 5, 6 and
6, 4, 6, 5, 6, 6. How many is that?
5, 6.
That is 6 out of 36. And then it said or, numbers are the same. How many where numbers are the same?
6.
1, 2, 3, 4, 5, 6. So we're adding another 6 out of 36. What's the catch?
There's 2 that are overlapping.
Yeah, what happened here? 5, 5, and 6, 6 fell into both groups, yes? Remember yesterday when we were talking about finding the area of that target and the starship? We had an area and an area, but then what did we have to do?
Subtract the overlap.
We had to subtract the overlap. How many overlapped here were
2.
2 of them. So we're going to subtract off 2 out of 36. So 636 plus 636 minus 236 is going to be
36.
1036. And 1036 will reduce to 5/18. Now, some of you may be saying, oh, I didn't add and subtract, I just counted. Could you do that? Could you look at, okay, we counted these original 6, yes? And then said, okay, I don't need to count those, I've already included those, so I'm at 6, 7, 8, 9, 10. Yeah, that's valid. This is the math behind it, okay? Use it or don't, it's whatever. But that's the legitimate math. Yes, it is equivalent to just counting them. Okay. And E. Probability, the numbers are different, or the sum is less than 6. Sum less than 36. That's going to be interesting. Okay. Numbers are different.
5 times 5.
How many numbers are different?
36 minus 6 is 30.
Yeah. So here's the deal. If the numbers are the same, was 6, how many are going to be different? That's going to be the other 30. Can we cheat on ourselves to do that? Yeah. You already did the math. You already did the, piece. So numbers are different is going to be 30 out of 36. What about the sum is less than 6? What do we have in the way of sum is less than 6? 1, 1, 1, 2, 1, 3, 1, 4.
2, 1, 2, 2, 2, 3. 3, 1, and 3, 2. And 4, 1.
Yeah. Notice the pattern shape here, yes? So how many numbers are how many sums are less than 6? I got 10. But
Minus
which ones are we gonna? Which ones did we double count?
1, 1, 2, 2.
Where the sum is less than 6 and the numbers are different. So that is 1, 2, 1, 3, 1, 4, 2, 3, 2, 1, 3, 1, 3, 2, and 4, 1. Those all got double counted in both groups, didn't they? How many is that? About 8. So you're subtracting off the overlap of 8?
32, 36.
So 30 plus 10 minus 8 is 32 36th. And 32 36 reduces to 8/9. Okay, guys. I don't remember if you use that setup necessarily in homework, but guys, this is common probability questions in math. Okay, being able to set up this chart and use it is good to know there. Notice on this one, okay, it was rolling a pair of dice. It wasn't two different events, it was just rolling a pair of dice and looking at what we're getting. Okay, this still falls under our mutually exclusive, non-mutually exclusive. As we move to the next page, we're going to start talking about independent versus not independent. Okay, so let's look at these examples. A jar contains 12 green marbles and 8 violet marbles. Marble is chosen at random from the jar and replaced. Another marble is chosen at random from the jar. Does the color of the first marble chosen affect the possible outcomes for the second marble chosen?
No.
You say no. Why not?
Because it gets replaced.
Okay, so you have to read carefully, folks. Key wording here is a marble is chosen at random from the jar and replaced. So you draw a marble out, you put it back, and then you draw a second marble. Does the probability change then? No. Okay, so does the color of the first marble affect the possible outcomes for the second marble? No, and that's because they are, I'm going to use the word independent. Okay. Independent events. I'm going to say independent events since first marble is replaced. Now, we have a couple probabilities to look at when you get done writing that. First question is probability of drawing a green marble on the first draw, and then a violet marble on the second draw. So what's the probability of drawing a green marble? 12 out of 20, yes? Because how many, do some basic math, how many total marbles are there? So 12 out of 20. Then the probability of drawing a violet marble. 8 out of 20, yes? Because you put that first marble back in, so we still have all 20 marbles, don't we? Okay, now, okay guys, this one's a little different in that everything else we've done, it was one roll of a die, or we roll a pair of dice, or we selected a ball. This one, we're doing what? We draw a marble, and then we have a second event, yes? We draw a second marble. So instead of adding, guess what? No? We're multiplying. When we start talking about independent and dependent, or independent and not independent events, you are multiplying when you have two different events going on. Now, you can multiply those big numbers if you want. My preference, though, is to reduce first. What is 12/20ths reduced to? (12/20ths reduces to 3/5. What is 8/20ths reduced to?
2/5.
2/5. And in order to multiply fractions, you're just going to multiply across. 3/5 times 2/5 is 6/25. Not too bad. So we're starting with some of the basics. Okay, change it up. What if we're doing the probability of violet and then violet? So what's the probability of drawing a violet marble on the first draw?
8/20.
Okay, 8/20ths. What's the probability of drawing a violet marble on the second draw?
8/20.
8/20ths, because what happened? We drew that first marble and
Then you put it back.
put it back. So you still have all 20 marbles. And we are multiplying. 8/20 times 8/20. Well, what is 8/20 reduced to? 2/5. 2/5 times 2/5 is 4/25. Okay. B. A marble is chosen at random from the jar and not replaced. Another marble is chosen at random from the jar. Does the color of the first marble chosen affect the possible outcomes for the second marble chosen?
Yes.
It's
Not
the-
replaced.
It's dependent.
Okay, so key phrase there. It says that marble is not replaced. So we have less marbles the second time around, don't we? Okay, so Jay used the word dependent. I think this book just says independent or not independent. So while I agree with the dependent, I'm going to write not independent. And it's not independent because, yeah, since first marble is replaced.
It's not replaced.
Yeah, that's what I said. Is not replaced. Thank you. Okay. We're being asked the same exact two questions as previous. So the probability of a green marble and then a violet marble. So, probability of a green marble on your first draw. What was it? 12 out of 20. Now,
8,
probability of a violet marble.
8/19.
Okay. The first marble was green. Okay, that's what they're asking us. We didn't put it back. So, instead of there being 20 marbles, there's now 19 marbles. We're going to assume that first marble was green, though. And so violet, all the violet are there. And so this is 8 out of 19. You are still multiplying because it's drawing, it's two separate events. 12/20 we can at least reduce, yes. 3/5. 8/19 does not reduce.
4/95.
Okay, multiply across. 24 95ths, which does not reduce. Okay. Violet then violet. So, now keep in mind, the new question, reset, all 20 marbles are back, yes? Okay, probability of drawing a violet marble.
8/20. I mean, yeah, 8/20.
8 out of 20. Then,
7/19.
probability the second marble will also be violet.
7/19.
Okay, instead of having all 20 marbles, that first violet marble I drew is still in my hand. So now I'm only picking from 19 marbles. And because it's violet followed by violet, we're going to assume there's one less violet marble. And so now there are 7 violet marbles and 19 total marbles. Okay? 8/20 we know reduces to 2/5. 7/19 does not appear to reduce. We end up with 14/95. Okay. Read carefully. They're not bad. You just have to read carefully. Okay. Go through the bottom set here. As you look at the bottom set, new scenario. There are 10 cards in a box, 5 black and 5 red. 2 cards are selected from the box, one at a time. In part A card is chosen at random and then replaced. Another card is chosen. Does the color of the first card chosen affect the possibilities of the second card chosen? Does the first card affect the second card?
Yes.
Gets replaced. No.
No.
Okay, so again, it all comes back to reading, doesn't it? Okay, a card is chosen at random and then replaced. So that means when you go to draw your second card, all the cards are there, yes? So is that first one going to affect the second one? And no. So I'm going to say, let's see, does the color of the first card chosen affect the possibilities of the second card chosen? Officially, no. And I'm just going to use the word independent, since first is replaced. Okay. Have you started in? Probability of a red. She says 5/10. 5 red cards out of total cards. Then, probability of black. 5/10 because that red card we just drew got replaced. Yes, it went back in. What do you know about 5/10? And 1/2 times 1/2 is 1/4. Okay. Probability of red than red. What's probability of red on the first draw?
5/10.
5/10. The card is replaced. So what's the probability of red on the second draw? 5/10. Deja vu, did we just do this? 5/10 reduces to be 1/2. 1/2 times 1/2 is 1/4. I'm always doing my reducing ahead because I'm not going to pick up the calculator unless I have to. Okay? Now, B. What's it say? Okay, a card is chosen at random and not replaced. Another card is chosen. Does the color of the first card chosen affect the possibilities of the second card chosen? Yes, it does.
It's dependent.
Yep. So, yes. Oops. Not independent. First is not replaced. Okay. Let's see how that changes things up here. Probability of red than black again. Probability of red?
5/10.
5 out of 10. Probability of black. Okay, are all 5 black going to be there?
No. I mean, yeah.
Yeah, because the first card we drew was a red card. Are all 10 cards going to be there? No, because that first card we drew. So 5/9. 5/10 is 1/2 times 5/9. 1/2 times 5/9 is 5/18. Okay. Can I just copy my answer and put 5/18 on this one?
No.
No, because that card is not replaced. It makes a difference, doesn't it? Okay. Probability of the first red.
5/10.
5/10.
4/9.
Okay. I draw a red. It's not replaced. So that means I'm holding a red card in my hand. That means there's only 4 red cards to pick from and only 9 total cards. 5/10 is 1/2 times 4/9. You can multiply across, or you can cross cancel and then multiply across. If I just multiply, it's 4/18, which reduces to 2/9. Okay. Okay. Every problem's a little bit different, and that's what we have to watch for. Now, what we just talked about were independent events, and the idea that if you have 2 events happening, independent, that you're going to multiply them. Okay? And that's what this next piece is saying. If A and B are independent, then the probability of A and B, you do probability of A times probability of B. This is just reversing what it's saying. We already talked about definition. Independent, when the outcome of one event does not affect the probability of a second event, the two events are independent. Okay? We just did some independent, didn't we? Here's another example of independent. Rolling a die and tossing a coin. Does what you roll in a die affect what you get when you flip the coin, or vice versa? No relation whatsoever, right? So, if we're being asked for the probability of rolling a 4 and flipping a heads, what's the probability of rolling a 4? 1/6, yes? What's the probability of flipping a coin and getting heads?
1/2.
Are we good with the 1/2? When you flip a coin, it's heads or tails, right? So heads is 1 out of the 2 options. How are you going to find the probability of rolling a 4 and flipping a heads? You're going to multiply. So 1/6 times 1/2, which is 1/12. Okay, basic there. Okay, let's look at a few other examples as time allows. May or may not get all the way through to the last example, but we'll try. Okay, let's talk about Alex. Alex cannot decide which shirt to wear today, so she chooses one at random. And then, totally separate fact, the probability of rain today is 40% or 2/5. 2 random facts, yes? Okay. Now, the question in A is, what is the probability that Alex chooses a yellow shirt and that it does not rain? Now, first of all, you can see my beautiful picture, yes? Do you need to label your picture because the colors didn't show up, did they? Okay, so realizing we've got a yellow shirt, a blue shirt, a yellow shirt, and a green shirt, yes? Okay. Now, with that in mind, probability that Alex chooses a yellow shirt and it does not rain today. So we're looking at probability, if I write out the notation of yellow and not raining. Again, sometimes you get questions in terms of words. Sometimes you're going to get them in the notation. So, probability of yellow. Okay, 2/4. There's 2 yellow shirts out of 4, which does indeed reduce to 1/2. Probability it does not rain today. Yes? Because what did they give us? Yeah, the probability of it raining. So the probability of not raining, well, the probability of raining is 2 out of 5, then the other 3 out of 5 is not raining, yes? Or we could say the other 60%. Okay. These 2 events, it's 2 separate events, yes?
Yeah.
So we're going to take these probabilities and we're going to multiply. 3/5 does not reduce. 1/2 times 3/5 is 3/10. Review. What is that as a decimal? Okay, 3/10 is the decimal 3/10 or 0.3. What is that as a percent? Multiply by 100. Move the decimal 2 places to the right. And it is 30%. Again, watch directions for how you have to express answers there. Now, the real reason we're getting to this problem. B gets a little more complicated. What is the probability that Alex chooses a yellow shirt and it does not rain today, or that Alex chooses a green shirt and it rains today? We have two different scenarios going on, right? And they want us to put them together. So the first scenario asks the probability that what?
The one that we just.
Okay. The probability of a yellow shirt and not raining. Now, can we cheat off of ourselves? That's what I call it. We already did that work. Do we need to redo the work? No, the probability of it yellow and not raining. Well, from up above, that is, I'm going to go with 3/10. Now, what's the other piece? Or that Alex does what? Chooses a green shirt and it rains. Have we done this one yet? No. So what's the probability that Alex chooses a green shirt? 1 green out of 4. And what's the probability that it rains? 2/5. Now, 1/4 and 2/5 we're going to multiply. 1/4 times 2/5 is, okay, I'm going to write 2/20 for the moment, but I do agree it's going to quickly become 1/10. Okay, guys, probability that Alex does this or this. What am I going to do with these two probabilities?
Add them together.
I'm going to add them. Okay, so you're finding the probability of each scenario, and then you're adding them together. So that means I'm adding 3/10 plus, what is 2/20? 1/10. 3/10 plus 1/10. 4/10? I'm wondering if the book wants a percent on this one, because I just have 4/10 equals blank percent. 4 out of 10 would be 40 out of 100, and so this is 40%. Again, you can always change it to a decimal by dividing, and then multiply by 100. Okay. Getting the idea, yes? Okay. Look at the spinner when you're ready. You spin this spinner 2 times. Assume that the probability of blue each spin is 1/3. Mine has colors. You guys have letters, right? So probability of B is 1/3. And the probability of orange each spin, labeled as O on yours, is 2/3. What's the probability of getting the same color both times? So what do we mean the same color?
Either 2 blue or 2 orange.
Okay, either 2 blue or 2 orange. So what's the probability of getting a blue followed by a blue, or the probability of getting orange followed by orange? Okay, what's the probability of getting blue the first time? 1/3, it told me, right? What's the probability of getting blue the second time? 1/3. Now, spinning the spinner twice. You spin the spinner once, you spin the spinner a second time. That's 2 separate events, yes? So since that's 2 separate events, we're going to take the 1/3 and the 1/3, and we're going to multiply. 1/3 times 1/3 is 1/9. Okay? Repeat the process for orange. What's the probability of getting an orange on the first go round? 2/3. If you spin again, what's the probability of getting orange? 2/3. 2/3 times 2/3 is 4/9. Okay. Take these two probabilities and you are adding them. 1/9 plus 4/9 is 5/9. And I just have that one as a fraction. Okay. On this bottom one, we'll do as much as we can. I don't guarantee we'll get through all of the pieces here because there's a little bit of talking, but we'll do the best we can. I will tell you right now what's on my brain. Homework is out there in Savas, okay? Get in there, do what you can do, figure out, any place you might be stuck. Tried to give you a variety of examples, but of course there's a variety of examples in Savas, so. Okay. Well, I have this labeled as extra example, don't I? Forgot about that. So I think it's one of those, then maybe if we don't get through it, it wasn't as hugely, I don't remember. Okay, anyways, it's a good probability question. A city issues 4-digit license plates for motorized scooters. The digits 0 through 9 are chosen at random by a computer program. What's the probability that a license plate meets each set of criteria? Okay, so 4 digits, yes? And each digit is chosen from 0 through 9. Now, what's the math trick here? What do you know about the number of digits from 0 to 9? 0 to 9 is 10 numbers. Think about it logically. 1 through 9 is 9. And so if you include 0, that makes it a 10th number. So just realize here that this is 10 digits. Okay? Now, license plates. What can my license plates be? Your very first license plate, if we start with digit 0, could be what? 0, 0, 0, 0. I'm not sure how many zeros I said there. All the way up to, what would the last license plate be? Okay. So those are your choices. How many options are there? Yeah. This is basically this 0 you have to add on at the end. This is 10,000 options. Okay? That's a lot, isn't it? Now, A is an easy question, if you let it be. The 4-digit number formed, so this 4-digit number formed, is odd. Is it that easy? Because here's the deal, guys. That last digit is a 50-50 chance, isn't it? The last digit could be even, or it could be odd. That's a 50-50 shot. So can you just say 1/2? Yeah. If you wanted to, you could say 5,000 out of 10,000. But easiest to say there is 1/2. Okay. The first number is not 3. Okay.
Anything that falls within the range of 3,000 is off limits.
Okay. So the first digit, that's all it's asking about. The first number is not 3. So if it's not 3, how many other choices are there? You're taking out one choice of 3, and there are 9 other options at work, right? So there, Savannah mentioned that you're taking out all the 3,000s. So she said 9,000 out of 10,000. I could go there. I also just thought of it as 9 out of 10. I shortcutted it that way. Because if you're thinking 9 out of 10, there's 9 options for the first number that work. Okay, I guess I do also have these in decimals, whatever. Okay. The first 2 digits are the same. So now you're looking at these first 2 digits are the same. How many times could that happen? Okay.
2 times.
Here's a couple different ways you can think about it. I thought of it as, okay, a 2-digit number is basically like from 1 to 100, yes? How many times does it happen that in a 2-digit number, the 2 numbers are the same? There's going to be what? Or you can think 0, 0, 1, 1, 2, 2, 3, 3, all the way up to 9, 9, yes? That's 10 numbers out of 100. You can think that way.
100 out of 1,000.
So you could also, yes, I agree.
Should be 110.
100 out of 1,000. Any way you look at this, it is 1/10. Okay, last one. All 4 digits are the same. What are your choices?
0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2. Happens 9 times.
Are you with her? Not 9 times,
10 times.
10 times, because it's
Yeah.
4 1s, 4 2s, all the way up to 9, and 4 zeros, which is 10 out of how many choices?
10,000.
All 10,000, which is 1 out of 1,000. Okay, guys. I know that was kind of quick. Working inside is done. Let me know. There might be some tricky ones. Okay, so working getting it done though.